Last lesson we discussed the magnetic field generated by an electric current. But we know that an electric current is caused by the motion of electric charges. Therefore, it is reasonable to assume that there is a magnetic field associated with a moving charge. And that's what we will be discussing in this lesson. A moving point charge is equivalent to an electric current, and therefore when moving charges constitute an electric current, the motion of charges generate a magnetic field. The magnetic field B at a point R from a point charge. Now we're going to have a quantitative expression. Suppose we have a charge Q. Let's say we need to find the magnetic field at this point due to this charge Q, and this Q, the charge Q is moving with a velocity V. The magnetic field generated by the motion of this charge at a point distance R, this distance is R, from that charge is given by B equal to mu 0 divided by 4 pi times QV over R squared. And we will be coming across this quantity quite a lot. Mu 0 is a quantity that we will see as we move on. So we got the magnetic field is directly proportional to the quantity Q times V and inversely proportional to the square of the distance from the moving charge to the point. And this distance R is a vector that points from Q to R. And mu 0 over 4 pi is the constant of proportionality, and mu 0 is called the permeability of free space. Now, towards the end of this lesson, we will talk more about this. Mu 0 has an exact value given by mu 0 equal to 4 pi times 10 to the negative 7 Tesla meter per ampere, which is the same as 4 pi times 10 to the negative 7 Newton per ampere squared. And this you need to keep in mind, so we will be using it very often as we go on. Now, what happens if theta is the angle between the velocity V and the vector R? Then the magnitude of B can be written as B equal to 10 to the power of negative 7. Now, where does this value come from? You know that mu 0 has an exact value 4 pi times 10 to the negative 7. If you divide this quantity by 4 pi, you get 10 to the negative 7. So mu 0 divided by 4 pi has an exact value of 10 to the negative 7. So, if theta is the angle between V, the velocity of the charge, and the vector R, then the field at that point, B, is 10 to the negative 7 times QV sine theta over R squared. Now, here is an illustration of the magnetic field produced by a moving charge. The moving charge, look at the vector R. The moving charge produces a magnetic field given at this point. Watch that carefully. Let's solve a simple problem. A point charge of magnitude 4.5 nanocoulomb is moving with a speed of V equal to 3.6 times 10 to the 7 meter per second along the line y equal to 3. Along that line, find the magnetic field at the origin produced by this charge when it is at the point negative 4, 3. Well, we have actually everything that we need to do this problem. First of all, At the instant when the charge is at this point, we need to obtain the vector r. What is the length of this vector r, where x equal to -4 and y equal to 3? The length of that vector r will be 5 meter. And if you know the length of that vector, now what is the angle theta between the vector r and the velocity v? How do you find that angle? Sine theta will be equal to 3/5, and therefore theta will be sine inverse of 0.6. Is that right? So we got the value of sine theta there, and b therefore is 10 to the -7 times qv sine theta over r squared. We know the value of q, we know the value of b, and we know the value of r, and that gives you the magnetic field as 3.89 times 10 to the -10 Tesla. Very simple problem. Well, what is the direction of this field? This field is perpendicular to both x and y axes and is directed along the negative z direction. In fact, the direction of this field is into the board, into the whiteboard that I'm using. So we can write b equal to -3.89 times 10 to the -10 Tesla K. Well, in the last lesson we discussed briefly about the magnetic field generated by an electric current. In this lesson we will make it more quantitative. We will obtain an expression for magnetic field due to current in a straight wire. Now, since current is caused by the motion of electric charges, it is obvious that if a wire is carrying a current, there will be a magnetic field around it. We saw that in the last class. Alright, let's consider a small length dl of a conductor carrying a current I. Here is a conductor carrying a current I in the upward direction here. And take a small length dl of that conductor. P is a point distance r from dl. Now here is the point P, and the distance of that point P from dl is r. And the r makes an angle theta with the direction of the current. The magnetic field dB at P due to the current I in the small due to the current in the small segment dl is given by dB equal to mu0/4 pi. Familiar? That is a constant of proportionality. I dl sine theta over r squared. Now, this is a very famous law in physics. And we're going to use this equation to generate expressions for magnetic field. So, if you consider a very small length of the conductor, the magnetic field due to current I in it will be mu0/4 pi I dl sine theta over r squared, where r is the distance of the point where this field is obtained from the length element. The direction of this magnetic field is at right angles to both the r vector and dl. So we got that expression back here. dB equal to mu0/4 pi I dl sine theta over r squared. Now, this equation is actually known as Biot-Savart law and can be used to obtain an expression for the magnetic field B at a point due to a straight wire. Now tell me, what does the magnetic field look like due to current in a straight wire like this? In the last lesson we talked about the right hand rule to find the direction of such a field. Is that right? The field will be concentric circles. Now, we can actually use the Biot-Savart rule to obtain an expression for the electric field at a point distance r from a conductor like this. So if I have a current I passing in this conductor, what is the electric field at a point distance r from it? It's given by B equal to mu 0 over 2 pi times I over r. I'm not going to give you the derivations of this. I'm going to give you simply those expressions. So you have a conductor that carries a current I, and if you take any plane, there is a magnetic field in that plane. And if you choose a point distance r from the conductor, this will be the amount of magnetic field at that point. And the direction of the magnetic field is given by the right-hand rule. You remember that one? Keep the thumb in the direction of the current, then the direction in which you grab the conductor with the other 4 fingers. So the magnetic field goes into the board on the right and out of the board on the left. Alright, let's do another example. A vertical wire on the side of a building carries a direct current of 12.5 ampere. What is the magnitude of the magnetic field inside the building at a distance of 20 centimeters from the wire? Now, we live in buildings which are wired all over. That means we actually live in a sea of magnetic fields. Well, we know that the magnetic field generated by current in a straight conductor at a distance r from it is mu 0 over 2 pi times I over r, and that is what we obtained in the previous slide. Now, that can be written in this case, I is 12.5 ampere and r is 0.2 meter. And so that's 1.25 times 10 to the negative 5 Tesla. It's a very direct application of the formula. Now, in that case, if you have 2 conductors carrying current, now each conductor has a magnetic field. Now, don't you expect that there will be a force between these 2 conductors? Well, let's look at the force between 2 parallel wires that carry a current. Now here I have 2 parallel wires, each carrying a current I, like this. There are 2 parallel conductors carrying a current I in the same direction. And if you now apply the law that you've learned, what is the direction of magnetic field due to the lower wire? If you use your right-hand rule, the field will go into the board below the wire and out of the board above it. Same in here, into the board below the wire and out above it. And so, if you notice the direction of the field in between, due to the lower wire, the field comes out of the board. Due to the upper wire, the field goes in. And as a result, the field in between the 2 wires is very weak. And the field outside the 2 wires is very strong. So you would expect the strong field will push the 2 wires into the region of weak field. So, if there are 2 parallel wires carrying current in the same direction, what kind of force would you expect between the 2 wires? You would expect that there will be an attraction between the 2 wires. Well, so as a result of the field due to each, there will be a force between them. The strength of the magnetic field produced by each wire is given by, now, you remember that equation? What's the equation for the strength of the magnetic field produced by a wire that carries a current I? is mu 0 over 2 pi times I over R. So this wire will produce a field mu 0 over 2 pi times I over R here, and this wire will produce the same field where the other wire is. Now, let me see if I can show you that on a web. As I illustrated earlier, if the currents are in the same direction, the field due to these two in between, if you notice, they are in the opposite direction, they cancel. So there are strong fields outside and a weak field inside that will produce a force that pulls the two wires together, or it is an attractive force. On the other hand, if equal currents are in the opposite direction, this time one wire carries current outwards and the other carries current inwards, you can see the field in between is very strong and the field outside is weak. Therefore, the strong field will repel the two wires. So, if you want to put it together now, you can now say if two wires carry currents in the same direction, there will be a force of attraction. If two wires carry currents in the opposite direction, there will be a force of repulsion between them. If you remember the expression for force exerted by a current carrying conductor that we discussed in the last lesson, we can say the force exerted by the bottom wire on the top wire will be IL times B, where I is the current, L is the length, and B is the magnetic field produced by the bottom wire at the top wire. So the force exerted by the bottom wire on the top wire is ILB, and therefore what is the force per unit length of the wire? If you now divide both sides by L, I get force per unit length will be I times B, and that will be B we know is mu 0 over 2 pi times I over R. Therefore, force per unit length of a wire in this case is I times mu 0 over 2 pi times I over R, and I get multiplied. We can write mu 0 over 2 pi times I squared over R. Now, as a result, each of the wire will experience a force due to the magnetic field of the other, and we explained how that happens. When the two wires carry currents in the same direction, there is a force of attraction, and when the currents are in the opposite direction, there is a force of repulsion. And I explained how that phenomenon occurs. Now, if the current in the left wire is I1 and the current in the right wire is I2, instead of the current being the same, if they are different currents, I1 and I2, then the force per unit length will be mu 0 over 2 pi times I1 I2 over R. If the currents are the same, both will be I, and we have I squared there. But if the currents are different, then this will be the equation. Alright, let's do a different problem. A horizontal wire carries a current of I1 equal to 80 ampere. A second parallel wire of mass per unit length of 0.12 gram per meter is situated 20 centimeter below it. What must be the current on this second wire so that it does not fall due to gravity? Well, we have a horizontal wire carries a current and a second wire is below it. Now, the situation here is the force of attraction between the two. There will be a force of attraction when the currents are in the same direction. The force of attraction between the two must balance the weights so that this will be suspended in the air due to that force. So what must be the current of the second wire so that the second wire will not fall due to the force of gravity? Well, this is a situation we have. We have a horizontal wire that carries a current of 80 ampere. And there is a second wire below it, a distance of 20 centimeter. We need to find the current in this wire such that the force of attraction between these two wires is exactly balanced by the weight of the bottom wire. Alright, we got I1 equal to 80 ampere. If I2 is the current in the lower wire, then what is the force per unit length on the lower wire? What's the equation for force per unit length? It's mu 0 over 2 pi I1 I2 over R. We got all these values except I2, is that right? Alright, and that will be mu 0 of course is 4 pi times 10 to the negative 7. I1 is 80 ampere and R is 0.2 meter, and that's equal to 8 times 10 to the negative 5 I2. This is the force per unit length. And this force per unit length must be equal to the weight per unit length of that wire. You are given the mass per unit length, therefore weight per unit length will be mass multiplied by G. That will be 0.00118 Newton. We can now take the weight per unit length of this wire and equate it to force per unit length, and we can calculate I2. What is therefore I2 equal to? I2 equal to 15 ampere. Well, we can use the concept of force between two parallel wires for giving a definition for the ampere. In fact, the original definition of ampere is obtained from such a situation. The force between two wires is used to give an exact definition for ampere, the unit for measuring current. Now, the equation for force per unit length of a wire when current flows in the same direction in two parallel wires separated by a distance r is, well, you know that, F over L, force per unit length, is mu 0 over 2 pi I1 I2 over R. Now, we're going to use this situation to obtain the definition of the ampere. What is 1 ampere? Suppose I1 is 1 ampere, I2 is 1 ampere, and R is 1 meter. So let's make that assumption. When I1 equal to I2 equal to 1 ampere and R equal to 1 meter, mu 0 we know is 4 pi times 10 to the negative 7. Now, if you use these values, what will be the force per unit length equal to? I replaced I1, I2 by 1 ampere, R by 1 meter. Of course, this is mu 0. And what is the value of force per unit length here? It is 2 times 10 to the negative 7 Newton per meter. Alright, can you now use this to define the ampere? What is the definition of ampere? We said if I1 equal to I2 equal to 1 ampere. So 1 ampere is the force. 1 ampere is defined as that current when flowing in each of two long parallel conductors separated by a distance 1 meter results in exactly a force of 2 times 10 to the negative 7 Newton per meter of length of each conductor. So, a current that flows in two parallel wires that are separated by 1 meter, that results in a force per unit length of this much is what we call 1 ampere. And that is the original definition of the ampere. Well, let's now talk about the magnetic field at the center of a circular loop. If I take a wire and bend it in the form of a loop, what is the magnetic field at the center of it? In order to find the magnetic field at the center of a circular loop, we take a small current element IDL that has a radius R. Now this is a circular loop. We take a small current element IDL on that loop. Now this is the current element IDL. And you know, we have talked about earlier that IDL is a vector. And we find the magnetic field due to that current element. Is that right? At its center. Now the magnetic field dB at the center of that loop due to this current element IDL. Can you write that equation from what we discussed in the earlier class? Will be dB equal to mu 0 over 4 pi IDL sine theta over r squared. It's actually Biot-Savart law. Alright, so the magnetic field at the center due to this small current element IDL is mu 0 over 4 pi IDL sine theta over r squared. There you are. Now, theta is the angle between the current element IDL and R. In this case, that theta is 90 degrees. Is that right? So, since the angle is 90 degrees, sine theta is 1. And therefore, we have dB equal to mu 0 over 4 pi IDL over r squared. And to find the total field at this point, we need to find the dBs due to all such current elements and add them all together. In other words, we do an integration. So we can say B equal to integral of dB, and integrating dB, what is dB equal to? Mu 0 over 4 pi IDL over r squared. Since sine theta equal to 1, we don't need to worry about it. And in here, mu 0 over 4 pi is a constant, r, the radius of the while loop, is a constant, and the only variable there is dl, the length of that small loop. So, we can take mu 0 I over 4 pi squared outside and integrate dl. What do you get if you integrate dl? Well, integration of dl will give you the total length of the loop, which will be 2 pi r, the circumference of that loop. Therefore, that will be mu 0 I over 4 pi squared times 2 pi r, or that will be mu 0 I over 2r. That's an important result. The magnetic field at the center of a current carrying loop of radius r is mu 0 I divided by 2r. Another example. 1/4 of a circular while loop carries a current I. Find the magnetic field at O, the center of the circular coil. Well, this time we have just 1/4 of a while loop. And that is the IDL that we're going to choose there. And the vector R is the radius of that loop. So the current element IDL is at a distance R from the center point O, and where R is the radius of that coil. The field dB due to one such current element is, how much is the field at the point O due to the current element IDL? will be dB equal to mu 0 over 4 pi I dl over r squared. What happened to sine theta? Sine theta is 1 because the theta is the angle between the vector IDL and the vector R, which is 90 degrees. Now the magnetic field at O, due to the entire length, will then be obtained by integrating dB for the entire length. In other words, integrating that dl. So that will be mu 0 over 4 pi I over r squared integral dl. And integrating dl here will be 1/4 of 2 pi r. Is that right? Because the whole of that will be a circle. This is only a quarter of the circle. And therefore we have mu 0 I over 4 pi r squared, this quantity, and integrating this will give you 1/4 of 2 pi r, 2 pi r divided by 4. And that will be mu 0 I over 8r. If you cannot see this on the screen, please refer to the printed PowerPoint slides. We will now obtain an expression for the magnetic field at a point on the axis of a circular loop of wire like this. Now, this is the circular coil and this is the axis. Any point on the axis is our subject. Alright, so we will start by considering a point. Consider a circular loop of wire of a radius r carrying a current I, and that is the axis of that circular loop. Let's take a point P on that axis, which is at a distance x from the center of that loop. Now, we will take a current element IDL. Our aim is to use the Biot-Savart law. Now, do you remember that law? We take a current element, say IDL, over here, and obtain the magnetic field dB at P. Then we will integrate that dB over the entire length of the circular loop. That is the idea. Now, you know from our earlier discussions, Biot-Savart law, the magnetic field at P due to the current element IDL will be mu 0 over 4 pi times IDL divided by r squared, where r is that distance. Now remember, this dB will be perpendicular to both r and IDL. That means sine theta equal to 1. Now, this r can be replaced. The square of this r is the radius big R squared plus x squared. So we're going to replace this r squared as big R squared plus x squared. That gives us the expression dB equal to mu 0 over 4 pi IDL over r squared plus x squared, where r is the radius of the circular loop. Now, very often in this lesson, sometimes in place of magnetic field, I mistakenly say electric field. If you hear that, substitute the electric field with magnetic field, because we are now studying the magnetic field due to an electric current. Now, this dB is actually in a direction such that the angle theta, which is the angle theta. Now, if you know this angle, you know that this angle is the same as that angle. Is that right? I think so. That means the dB makes an angle theta with the vertical. Now that means dB has an x component which I call dbx and a y component dby. Now, when you take a current element on the top, that is what we have done, it has this x component and this y component. How about you consider a current element diametrically opposite? If you take a current element here, dB will be somewhere in this direction. It has an x component and a y component. Now notice that for this element, if the y component is positive, for a current element here, the y component will be negative. For each current element, there is a corresponding element diametrically opposite, so that the y component of dB will all cancel. That means only the x component will survive. Alright, so a similar current element diametrically opposite to this one will produce a field dB at P such that it has an x component dBx and a y component dBy, and all the x components are in the same direction, but the y components will all cancel. They will not survive. And so we need only worry about the x component, which is dB sine theta. If this angle is theta, the x component will be dB sine theta. Well, dB we know is mu 0 over 4 pi times I dl over r squared plus x squared, and sine theta from this diagram is r divided by the small r, and this distance is square root of r squared plus x squared. So this expression replaces sine theta. Sine theta is r over square root of r squared plus x squared. Now combine all these, that will give you mu 0 I r divided by 4 pi times r squared plus x squared to the power of 3 over 2 times dl. All these quantities are constant, so we need only integrate for dl. So the net field B is obtained by integrating this dB along the length of the circular loop. Alright, let's do that. So B will be equal to this quantity that remains a constant times integral dl. And what does integral dl give you? The total length around the loop, which is 2 pi times capital R. And simplify that, it gives you this expression, mu 0 I r squared over 2 times r squared plus x squared to the power of 3 over 2. Now, this is the exact expression for the field at a point at a distance x. Let's consider a case where this x is very large compared to this radius r. In that case, this r can be ignored, and therefore the quantity r squared plus x squared to the power of 3 over 2 will simply become x cubed. Is that right? And so we have an approximate expression for the magnetic field at a large distance from a circular loop of wire as mu 0 I r squared over 2x cubed. If you remember, this is similar to the situation we discussed in static electricity. Okay, let's use this to solve the problem. A single loop of wire of radius 5 centimeter carries a current of 3.2 ampere. What is the magnitude of the magnetic field on the axis of the loop? 1 at its center. Well, that is the earlier case that we had considered. 2 at 2.5 centimeter from the center. We got to use the exact formula there. 75 centimeter from the center. Well, 75 centimeter, x equal to 75 centimeter is very large when compared to the radius 5 centimeter. We will use the approximate formula there. So all we need to do is use the appropriate formula for each of those. Field at the center of the loop is mu 0 I over 2r, and we have all those values, substitute them, and that gives you the field at the center of the loop. Second case, the field at a point 1 centimeter from the center. Well, that's a small error that I made. I have used 2.5 centimeter here, and I used 1 centimeter here. So what I suggest you do is correct that to 1 centimeter. So, what is the field at 1 centimeter from the center? We use the exact formula, where we know the radius, x equal to 1 centimeter, which is 0.01 meter, and substitute all the given values, knowing that mu 0 is 4 pi times 10 to the negative 7 Tesla meter per ampere, and that gives you the magnetic field at that point, 4.65 times 10 to the negative 5 Tesla. And finally, the field at 75 centimeter, we use the approximate formula, mu 0 I r squared over 2x cubed, and that gives you 3.49 times 10 to the negative 9 Tesla. So this kind of problems, very simple and straightforward. We will now discuss a law called Ampere's rule. Ampere's rule. Now, Ampere's rule is similar to Gauss's law in static electricity. You remember the net flux crossing an area is 4 pi k times q inside. Now, let's develop the Ampere's rule using the results we already know. The equation for the magnetic field produced by a current in a long straight wire, you recall that, is B equal to mu 0 I over 2 pi r, where r is the distance of the point where the field is discussed. Now, Ampere's law gives us a general relation between current in a wire of any shape and the magnetic field it produces. Now, I'm going to read the law and then interpret it. Ampere's law states that for any closed loop path, now here I have a diagram, here is a conductor that is carrying a current I, and what all we need to do is take any closed loop path around that conductor. Now that's what the law is talking about. Ampere's law states that for any closed loop path, the sum of the length elements times the magnetic field in the direction of the length element. Now remember, if you take a closed path around this conductor that carries a current, there will be a magnetic field anywhere along that length. Now, in order to take Ampere's law, the field must be in a direction parallel to the length element we take. For example, here I have taken a length element delta L, and we need to therefore take the component of B along that delta L. That means you take delta L multiplied by B that is parallel to that delta L. And you do that for each element and add them all together. That's what this means. Summation of B parallel times delta L. The sum of the length elements times the magnetic field in the direction of the length element is equal to the permeability times the electric current enclosed in the loop. So summation B parallel times delta L is mu 0 I. If you cannot see this on the screen, the right side of the equation is mu 0 I, permeability times the electric current enclosed in the loop. If this is the loop, the electric current enclosed in the loop is that I. Now this law is analogous to Gauss's law we talked about. Now Ampere's law can be expressed as a path integral. What's the meaning of a path integral? Integrate along the path. Now summation B parallel times delta L is actually integrate along the path of B parallel dl. So that will be integrate B dl, same as this. The summation is replaced by integral over the path of B dl equal to mu 0 I, and that is the statement of Ampere's rule. Let's do a small problem. Two long wires are oriented so that they are perpendicular to each other. One carries a current of 20 ampere in the positive z direction, and the other carries a current of 5 ampere in the positive x direction. At their closest, they are 20 centimeter apart. Calculate the magnitude of the magnetic field at B. Magnetic field B at a point midway between them. Now, here, this is the situation. This is the wire that comes out of the board. We would say into the board is negative Z, out of the board is positive Z. And there is another wire 20 centimeters below it, like this, which is carrying a current in the x direction. Well, let's draw that diagram. Now, this is the situation. This is the conductor that carries a current of 20 ampere in the positive z direction. It comes out of the board. And this is the conductor that is carrying a current of 5 ampere in the positive x direction. We need to find the magnetic field at P midway between them. Alright, let's use the equations that we developed so far to do this. So the top wire carries a current of 20 ampere out of the paper or out of the board in the positive z direction, and the bottom wire carries a current of 5 ampere in the positive x direction. The field P due to the current in the top wire, can you use the right hand rule and tell me what will be the direction of the field at this P due to the current in here? You see, the current is coming out towards you. So I'm going to stand here. I'm going to keep my thumb pointing at you. Can you see that? And I'm holding the wire like this. That means the field will be like this, going in the positive x direction. So the field due to this wire will be in the positive x direction. How about the field due to the current in this wire? The current is that way, so I'm going to keep my thumb pointing that way, and I'm going to wrap my finger. Look at the way it's coming out. It's going to come out of the board. It's going to come in the positive z direction. So the field at P due to the current in the top wire is in the positive x direction, and the field at P due to the current in the bottom wire is in the positive z direction. That means you need to find the resultant of those two. And the field at P due to the current in the top wire, use the equation mu 0 I over 2 pi r, where I is 10 centimeter and the current is 20 ampere, and that is 4 times 10 to the negative 5 Tesla in the positive x direction. Similarly, field due to this wire will be the same equation, where I equal to 20 amp, where I equal to 5 ampere. Is that right? You need to correct that. The bottom wire carries a current of 5 ampere, and the distance r is 0.1 meter. That change, so the field at P due to the bottom wire is 1 times 10 to the negative 5, a quarter of that. And therefore, what is the resultant field at P due to both? This is the field due to the top wire. This is the field due to the bottom wire. So the resultant will be, therefore, square root of 4 times 10 to the 5 squared plus 1 times 10 to the negative 5 squared. That is 4.12 times 10 to the negative 5 Tesla. Alright, let's now look at what is called a solenoid. What is a solenoid? Now what I have here is a solenoid. It is made up of a number of wire loops. Now what we're talking about so far is the field. Earlier on we obtained an expression for the field at the center of a loop of wire. Now if you have several of those loops continuously wound on a frame, that is a solenoid. Now if you look at this, on the side that faces me, if the current goes up, the side that faces you, the current will go down. So if you use the right hand rule, let's work out the direction of the magnetic field when a current flows in this. If on my side the current goes up, I will wrap my fingers. See this? My fingers goes in on the right side, that is my right side, and comes out on the left. Now, on your side the current goes down. So, look at that again. The current goes down. Wrap your fingers. My fingers goes in on the right and out on the left. And that's how the magnetic field of the solenoid is going to look like. So, each side of a turn can be approximated as a straight wire carrying current. If on one side the current is up, the other side the current will be down. So the net field due to all these turns will be the resultant of the field produced by all these turns inside the solenoid. Now here I have a picture of that. Now you remember I've told you if the current goes up here, then the field will go, look at the way again, the field will go inside on the right and outside on the left. In the same way on the other side, again the field will go inside on the right and outside on the left. The result is you have a bar magnet here, is that right? Where the field enters the right and leaves the left. That means this end behaves like a south pole and this end behaves like a north pole. So the solenoid is like a bar magnet with a north pole where the current flows in the counterclockwise direction. If I stand here and trace the direction, look at that, the direction of the current is counterclockwise and that end is positive. If I stand here, the current will be clockwise when I look. So when you look from one side and trace the current, if the current flows counterclockwise, that end will be a north pole, and if the current flows clockwise, that end will be a south pole. Now this is actually an example of an electromagnet. You can see the field outside is rather weak and the field inside is very strong. Now using Ampere's rule, we can actually obtain an expression for the field inside the solenoid. I want you to watch the field lines inside. What can you say about the magnetic field inside the solenoid? All the field lines are parallel. That means the field inside the solenoid is a uniform field. It's a constant anywhere. And outside it is very weak. Now, using Ampere's rule, we can show that the field at any point inside a solenoid is B equal to mu 0 Ni, where N is the number of turns per unit length. number of turns per unit length. Don't confuse that. So n is the number of turns per unit length of the solenoid. Now notice here that B is uniform inside the solenoid and depends only on the number of turns per unit length and the current in the solenoid. Let's do an example. A thin 10 centimeter long solenoid has 400 turns and carries a current of 2 ampere. Calculate the magnetic field inside the solenoid. Well, what all we need is mu0, n and I. The total number of turns is 400 and the length is 10 centimeter. Therefore, what is the number of turns per unit length? Is the number of turns divided by the length, and that will be 4,000 turns per meter. And now we can use that formula right away. B, the field inside that solenoid, is mu0 Ni, and that will be 0.01 Tesla. Okay. A current carrying solenoid is actually an electromagnet. You can see this is an electromagnet, which is a solenoid, and this is a bar magnet, and look at the similarity. They are both almost the same. And such electromagnets are used as switches and relays in many electrical circuits, such as VCRs, automobile starters. You can see in all such electrical devices, these electromagnets play a very important role. So, if you want, you can actually go and study deeper by Googling electromagnets and their applications. Alright? Alright. Let's now wind up this lesson by talking about some theory about magnetism. You remember in the beginning of the last lesson I said all magnetic materials are made of these minute, tiny atomic magnets. And we call them dipoles, is that right? Made up of a north pole and a south pole. There are no magnetic monopoles. Now, what is the origin of magnetism? That is what we're going to discuss here. Now, an electric charge in motion produces a magnetic field. That's what we've been discussing so far. If an electric charge is moving, it has a magnetic field associated with it. Now, you know that an electron is a spinning object. So, an electron that carries an electric charge is spinning, means it has a magnetic field around it. So, an electron carries a charge and a spin. It can be considered as a charge in motion, and so it has a magnetic field around it. In many atoms, electrons are paired in energy levels so that the magnetic field caused by one electron is cancelled by the magnetic field caused by the other electron, because their spins are in the opposite directions. But in some materials which has some unpaired electrons, those magnetic fields will not cancel. There will be some net magnetic field, and that can be influenced by external magnetic field. And also, if there are more electrons with spin in one direction than in the other, the atom will carry a net magnetic field. And this is the origin of the magnetic dipoles. Now, such an atom has a net magnetic moment. In some materials, these magnetic moments tend to align with one another, forming what are called magnetic domains. So, in some materials, most of these magnetic moments will align themselves to form domains. But ordinarily, the material will not exhibit magnetism because these domains are randomly organized. The direction of alignment varies from domain to domain. Now, here is an example. Here is the alignment inside one domain, and here is the alignment in another domain. If you take the behavior of the entire material, the net magnetism is zero because of the random arrangement of the magnetic moments forming the domains. Here is another example of this random arrangement of domains. But the moment you subject this material to an external magnetic field, all these magnetic moments, all these domains will align in the direction of the magnetic field like this, the diagram on the right. That means when a magnetic material like this is subjected to a magnetizing force is an external field. These magnetic moments will align themselves in the direction of the external field, making that object a magnet. So, when placed in an external magnetic field, the magnetic moments of the domain align in the direction of the magnetic field, producing a net magnetism in the material. Now, the extent of magnetization actually varies from material to material, and we use the term called permeability of the material to describe the extent of magnetization of a material when it is subjected to a magnetizing force. So we will now talk a bit about the meaning of permeability. Now, we have actually used it. The magnetic permeability of free space is what we call mu zero. Don't you remember that? Mu zero divided by 4 pi we used as the constant of proportionality. That mu zero is the permeability of free space, and you know it has a value 4 pi times 10 to the negative 7 Tesla meter per ampere. Now, most materials can be classified based on their magnetic properties as ferromagnetic, paramagnetic, and diamagnetic. Well, we will look at each of these briefly before we move on. Alright, what are ferromagnetic materials? Ferro is iron, is that right? Now, these materials exhibit a strong attraction to magnetic fields and are able to retain their magnetic properties after external field has been removed. That means they will respond to the external magnetic field very strongly, and the domains will align themselves to a very large degree. And even when the external field is removed, some of the alignment will be retained. Such a material is a ferromagnetic material. They are very good magnetic materials. Now, in the domains of these materials, large numbers of atomic moments of the order of 10 to the 12 to 10 to the 15 are aligned parallel so that the magnetic force within the domain is very strong. In the unmagnetized state, the magnetic moments of the domains are randomly oriented, and when a magnetizing force is applied, the domains become aligned, producing a strong magnetic field within that material. Now, the permeability mu of a ferromagnetic material actually depends on the strength of the external magnetizing field. So there is no particular value you can assign to a ferromagnetic material. What that means is mu for a ferromagnetic material is not a fixed value. It depends on the external magnetizing material. Examples are iron, nickel, cobalt, and so on. What are paramagnetic materials? Well, these are materials which will respond to a certain degree, but the extent of magnetization is not very strong. Now, the paramagnetic properties are again due to the presence of some unpaired electrons and from the realignment of the electron orbits caused by the external field. And they have permeability values slightly greater than mu zero, the permeability of free space. Not very strongly magnetic. And these materials include magnesium, molybdenum, lithium, and tantalum, and so on. How about diamagnetic materials? These are materials that exhibit actually a negative magnetism. Well, diamagnetic materials are slightly repelled by magnetic field, and the material does not retain the magnetic properties when the external field is removed. Diamagnetic materials are solids with all paired electrons, resulting in no permanent net magnetic moment. Now, we have examples of that will be most of the materials that we know, copper, silver, gold, they're all diamagnetic, and their permeability will be slightly less than mu0. Alright, so we have ferromagnetic materials who have no fixed permeability value. Diamagnetic materials have permeability values less than mu0, paramagnetic slightly greater than mu0. And this leads us to another important term in magnetism, that is magnetic susceptibility. Alright, we know that all materials exhibit magnetism to some extent. The value of the magnetic permeability mu of a material determines the extent to which a material acquires magnetism in the presence of an external field. Is that right? Well, therefore, the ratio of mu divided by mu0, permeability of the material divided by permeability of free space, is an important term, and it is called a relative permeability. It actually compares the magnetic properties of a material with that of free space. So what is relative permeability? It is mu divided by mu0, and we represent relative permeability by K sub m. So K sub m is mu divided by mu0. Now tell me, for a paramagnetic material, because mu is slightly greater than mu0, Km is slightly greater than 1. But for paramagnetic, it is slightly less than 1. Is that right? Now, the magnetic susceptibility, chi m, susceptibility is represented by the Greek letter. Look at the way I read it, chi sub m, chi m. Now, we use Km to define chi m as chi m equal to Km minus 1. Magnetic susceptibility equal to the relative permeability minus 1. Now that means paramagnetic substances have Km slightly greater than 1, therefore the susceptibility of a paramagnetic material is positive. How about diamagnetic materials? Their Km is slightly less than 1, therefore chi m will be negative. How about ferromagnetic materials? Well, they have positive susceptibility, but they have no fixed values because the permeability depends on the external magnetizing field. Well, that brings us to the end of this lesson with a discussion on hysteresis loop. What does that talk about? It talks about the way we magnetize a material. In order to magnetize a material, we use a magnetizing field. You see, if I bring a magnet close to a magnetic material, the magnetic material becomes a magnet. Now, here is a magnetic material. This is not a magnet, but this is a magnet. I can magnetize this by subjecting this to a magnetic field. You can see as I bring it closer and closer, the extent of magnetization in this material will increase. Now, as I bring it closer, I can feel it. It's actually pulling me. So, the extent of magnetization, that means the magnetic flux that is created in here increases as the magnetic as the magnetizing force increases. So the magnetization of a magnetic material increases as the magnetizing force increases. Now, hysteresis loop is actually a diagram that shows the amount of magnetization in a magnetic material compared to the external magnetizing field. Now you can see how strong it is. Now, mostly the external magnetizing field is changed by using an electric current. So a plot of induced magnetic flux B, the magnetic flux generated in the magnetic material, versus the magnetizing force H is called the hysteresis loop. And here I have a diagram of that. Now we're going to start here, where the magnetizing force is 0 and the flux, the induced magnetic flux also is 0. So that's the situation that we actually started with. Now, this is so strong. Now, if it is so far, that is where we are here. Now, I'm going to increase the magnetizing force. The magnetizing force increases, the induced magnetic flux also increases. Now, so this is where we start, and we increase the magnetizing force, the magnetic flux induced increases, and this is the path until we reach a saturation point. What does saturation mean? All the magnetic domains are aligned and it has reached a saturation and you cannot attain any more magnetization. Now, if you decrease the magnetizing force, now what happens? The aligned magnetic domains will begin to disalign, and when the magnetizing force is 0, the induced magnetization does not return to 0. A certain amount of magnetism is retained. So for a particular value of H, the magnetic flux density reaches a saturation value. If now H is reduced, B will also be reduced, but not along the same path. That means certain amount of magnetism is retained. When H is 0, that is H is brought back to 0, the curve will move from point A to point B. At this point, it can be seen that some magnetic flux remains in the material, even though magnetizing force is 0. Now remember, this discussion is purely for ferromagnetic materials, which retain some magnetism even when the magnetizing force is removed. What happens if you now increase the magnetizing force in the negative direction? Now, as I told you, the magnetizing force is actually a current. If you pass current in one direction, you have magnetizing force in one direction. If you reverse the current, you have a reverse magnetizing force. If you reverse the magnetizing force, the domains are brought back to 0. That means the magnetization here is 0. But it's 0 not when the magnetizing force is 0. So let's talk about this before we come to that. What do you call this point? This is the point where the magnetizing force is 0, but certain amount of magnetization is retained. We call that point the point of retentivity. Alright. As the magnetizing force is reversed, the curve moves to a point C where the flux has been now reduced to 0. Now, this is called the point of coercivity. That means the reverse to magnetizing force has flipped enough of the domains so that the net flux in the material is now 0. The force required, what's this one? The force required to move the residual magnetism from the material to 0 is called the coercive force. The coercive force is the force required to move the residual magnetism back to zero. And that's why this is called the coercivity. And now, if the magnetizing force is sufficiently increased in the negative direction, then all the domains will be aligned in the opposite direction and will reach saturation. And you can retrace that path. So reducing H to 0, bring the curve back to E, and then increasing H in the positive direction will return it to point F, and of course the loop can be completed. Now you can see the loop does not really follow the same path. Well, that actually clearly indicates about the retentivity of magnetism of a ferromagnetic materials. Well, I'm going to stop this lesson here, and we will talk more about magnetism and properties of magnets in the next lesson.